So in Chapter 8, you're going to be looking at comparing two groups of data versus just testing one single mean or one single proportion. So we're going to start in Section 8.1, testing the difference between means. Now we're going to see a few different tests that we can use to test for the difference between means. We're starting here with what's called the z-test. And what's going to be really important for you in Chapter 8 is knowing when to use each test. So we will use the z-test, what we're looking at here, whenever we have independent samples. That means one is not related to the other, one does not affect the other. It means nothing is paired up. And we also have to have known values of sigma. Now what's important to note here is when this says that sigma must be known, you probably already understand that sigma is a standard deviation. But what's important to note here is you can only use the z-test when you know the population standard deviation. So if you just have a sample standard deviation, you're not going to be able to use this z-test. All right, you have to know the population standard deviation for your two groups. All right, now, two things that we're checking here. We talked at length about, sigma 1 and sigma 2 and what that represents. The other part of this, though, is making sure that we have independent samples. All right, now, you've got a definition down here, and I kind of told you it's one does not have an effect on the other. So let's just start with a few examples, making sure that we can determine when we have independent versus dependent samples. All right, so in our first example right here, our two groups, we have the weights of 65 college students before their freshman year and weights of the same 65 college students after their freshman year. Now, I'll tell you, there's a couple of things to note here. The big one is that you are pulling data from the same set of students. All right, what that means is for each student, you will have a pair of values. One will be their before value, and one will be their after value. That lets you know that these two things are related. The weight of a person before is going to be directly related to the weight of a person after. Anytime you have paired data like this, and it's very common to see it with a before and after situation, that will always represent a dependent sample. And when you have a dependent sample, this is not the test that you're going to use. Now, if we compare this to our second example, we're looking at test scores. So we have scores for 38 adult males. And then we turn around and look at 50 adult females. Now the thing to note here is this is two completely separate groups. We're not looking at test scores for the same 38 males. We're looking at test scores for males, test scores for females. These two things are not related. Nothing is paired up. This is what we call independent samples, which is the type of samples that we're going to be looking at in this hypothesis test. All right, so real quick, just two additional examples here. We have blood pressures. We look at the blood pressures for 30 adult females, and then we turn around and look at the blood pressures for 30 adult males. Again, two separate groups. Nothing is paired up. That's an example of independent samples. Versus our second one, where we look at the midterm exam scores of 14 chemistry students, midterm exam scores, and then we turn around and look at the final exam scores for the exact same set of students. That means each student will have a pair. They'll have a midterm score and a final exam score, and anytime we have paired data, we have dependent samples, which will use a different hypothesis test. All right, so again, this is the test, we call it the z-test, for independent samples. So just a little bit of summary here as far as notation, all right, how you're going to see things represented. mu1, mu2, those are population means. And then sample data, x bar is the mean, s is a sample standard deviation, and n is our sample size. And every hypothesis test that we run is going to be set up in one of three ways. All right, we will either be testing for a difference. All right, that's just one is not equal to the other. Or we could test for a more specific difference where mu1 is greater than mu2, one means bigger than the other, or where mu1 is less than mu2. All right, now remember you must know your population standard deviation if you are going to use this particular hypothesis test. The reason you must know your population standard deviation is because that will allow you to use the standard normal distribution to find your critical values. All right, now remember, anytime you need tables, I always link those for you within the section. So for example, if you go to Chapter 8, Section 8.1, then you'll notice right up here, you have a link to your standard normal table. All right, now, once we find our critical values and rejection regions, very similar to what you did in Chapter 7, we will calculate that standardized test statistic. Now, the main thing to note here, you will look at the difference between your sample means. This value that you're seeing right here, the difference between your population means, you're always going to be testing against a difference of 0. So it's technically part of the formula, but it won't play a part in the value that you're calculating. And then you'll divide the difference between your sample means by the standard deviation for the difference between those means. That's how you always standardize something. You subtract its population mean, you divide by its standard deviation. And then same decision rule that you've been using. If you're in the shaded region, reject the null hypothesis. If you're not, you fail to reject. All right, so here's our example. First thing I'm going to do is just look at my claim, look at the sample data that I have, just kind of write down everything that I know. So if I read through the information given here, I've got survey data. The survey data here looks at 2 separate groups. All right, so notice I've got information about annual wages for local governments. All right, there's my mean, my sample size, and my standard deviation. Now, I'm going to go ahead and write down what I have here on my group 1, which is the local. And I'm just calling that group 1 because it comes first. It doesn't really matter. But again, I've got a sample mean, so I'll call that X bar 1, of 55,950. I've got a sample size, which will be N1, of 100. And then very careful here, notice you are given population standard deviation. That's really important because you can only use Z if you know the population standard deviation. So if this standard deviation was only for that sample of 100, it would not be sigma and you could not use the Z test. But because it represents the entire population, it is a value of sigma, and I'm going to label it as sigma 1. Now, my other group, what I'm going to be comparing this to are the annual wages for state governments. So again, I'm going to do the same thing. I'm going to write down those 3 values that I'm going to need to run the test. I have a sample mean, call this X bar 2, of $51,100. I have a sample size of 100 again. These 2 samples have the same size. And then again, population standard deviation. That's going to be sigma 2 is $5,575. All right. Now, this problem comes right out and tells me that these are independent. But even if it didn't come right out and tell me that these 2 things were independent, I would say, all right, well, these are 2 separate groups. We've got local, we've got state. We're not pairing things up. And so I could kind of tell for myself that these were independent as well. But what's important here, I have independent samples. I know the population standard deviations, sigma 1 and sigma 2. Therefore, I'm going to use a z-test to test the difference between the two. All right. Now, as far as what I'm testing, my claim here, is there enough evidence to conclude that there is a difference? So when I go to write down my claim here, just to identify what I'm testing, a difference between the two things, it's not saying one's larger or greater than or less than, it's just saying there is a difference. So this would just be written as mu1 is not equal to mu2. So just write down your claim. You know, it might be greater than, it might be less than, but identify that in terms of mu1 and mu2. And then what you want to remember as far as setting up your hypothesis test correctly, statements that are in the null hypothesis must contain equality. So in that null hypothesis, you can only put equal to, less than or equal to, greater than or equal to. All right? We don't have that in our claim. Our claim has inequality, so it's going to go to the alternative hypothesis. All right? Equality null, inequality alternative. And once you place that claim, the other statement has to be the opposite of that claim. So that means in my null, mu1 is equal to mu2. All right, and these tests are always going to be set up that same way. And then I'm just going to make a note for myself here that my claim, what I was asked to test, is in the alternative because we're looking for a difference, not equal to. All right, now that's my first step, set everything up. My second step is to get my critical values and my rejection region. And based on the fact that I have population standard deviations and independent samples, I'm going to find the rejection region and the critical values using the standard normal curve. So I'm just going to sketch out my little bell-shaped curve here. Now remember, to figure out if you shade left side, right side, or both, you always look at the alternative hypothesis, and it will tell you. So less than here would shade left, greater than here would shade right, and a not equal to here means I'm going to have a two-tailed test, and I'm going to shade on both sides of the curve. So I'm going to come down here and shade the rejection region for a two-tailed test, half of it in the left tail, half of it in the right tail, and I'm going to remember that my level of significance, which is sitting right up here, always gives me the area of the shaded rejection region. Now, if it's a left or a right, then I'll use the full level of significance at 0.10. When it's a two-tailed test, because my rejection region is split, I'm going to look at alpha over 2, right? 0.10 divided by 2, which means I'm actually going to use an area of 0.05 to find my critical value. All right, now I'm going to go to my standard normal table. And again, I linked that for you on the page for section 8.1. And I'm going to look for that alpha over 2 that I just calculated of 0.05 as an area. So I'm going to look inside the table. Anytime I'm looking inside the table, I like to go ahead and write it to 4 decimal places just to remind me of exactly what I'm looking for. Now, right now I'm on the side with positive z's, and you can see that my areas here go no lower than 0.5. So I'm going to need to refer back to the negative side of this table in order to find an area of 0.05. Now, I'm going to search through my areas. Typically what I do is I take the area that gets the closest to 0.05. Now, this is kind of a special case. Right, 0.0495 and 0.0505, those are equally spaced from 0.05. So I can't take one as closer than the other. What I do in that case is I take each one, right? So the z-score that corresponds here would be 1.65, and the z-score that corresponds here would be 1.64, and I take their average. I just take the value that's halfway in between, which here is going to be a negative 1.645. All right, so that's going to give me a negative critical value here. And then the positive, all right, all I'll have to do is change the sign to get the value on the right side, which is 1.645. Now, if you've been using a different method, if you use maybe the inverse normal on your calculator to get critical values for Z, if you use the normal calculator in Statcrunch to get critical values for Z, those are fine to use here as well, right? Either one's going to give you the same critical value as you would find using your table. All right, now, I've got my rejection region, so let's just kind of look back for a minute and see where we are. Right, we set up our null and alternative. We just found our critical values in our rejection region. So what we need to do now is calculate that standardized test statistic. Now remember, the difference between mu1 and mu2, we're using 0 because we're comparing. So all you're going to have to do here is look at the difference between your sample means and then divide that by the standard deviation. Okay, so when I go to calculate my standardized test statistic, I'm going to take the difference between the sample means, and then I'm going to divide that by the standard deviation of this difference. And that standard deviation is going to take sigma 1 squared divided by its sample size plus sigma 2 squared divided by its sample size, and then take the square root. All right, so based on all the data that we wrote down at the beginning, we're going to take our first sample mean of 55,950. We're going to subtract the sample mean for the second group, which is 51,100. And then using the population standard deviation, which again is required here if you're going to use Z, sigma 1 is 6,200. I'm going to square it and divide by its sample size. Sigma 2 is 5,575. I'm going to square it, divide by its sample size, and then take the square root. Now, be careful when you calculate here. You may need to work this out in steps or just make sure that you're careful with your parentheses. But in this case, you should end up with a standardized test statistic of 5.82. So if I take that back up here, all right, compare it to my rejection region, 5.82 is definitely past 1.645. It's going to be somewhere way up here. What's important is that it's in the shaded region. All right, anytime you're in the shaded region, what that tells you is that you should reject the null hypothesis. If I were in the unshaded region, the only difference would be my test fails, and I would state failed to reject the null hypothesis. Now, your last step is to interpret the results or make sure you answer the question that's being asked here. Is there enough evidence to conclude that there is a difference? Right? So our decision here said reject the null hypothesis. It says that's wrong. And anytime you reject the null hypothesis, the alternative has to be true because it's the opposite. So if we're rejecting mu1 equal to mu2, then we're saying, yeah, there is a difference between the two if that null hypothesis must be rejected. So the answer to the question here would be yes. More specifically, there is enough evidence to support. Another thing to remember is if your claim is in the alternative, you're always going to talk about whether or not you can support it. All right, and that's what we have here as a claim in the alternative. So yes, there is enough evidence to support that claim. All right, now, just one more quick thing here. You do have access to these hypothesis tests in Statcrunch. They're not going to do everything for you, but they will allow you to quickly calculate your test statistic and also to get the p-value if you happen to be asked for that. So if I take this information to Statcrunch, and you guys know you can open it up from within any homework problem. You can also access it from the main course menu under Student Resources. So that's where I'm going to go. Now, if you have actual data values, you can go ahead and load those right into Statcrunch, and you can calculate from the actual data values. In this case, I just have the summary stats. So I'm just going to open up a blank Statcrunch sheet. I just went to Open Statcrunch because I'm going to be typing in the summary information myself. Now, what I'm going to do here is go to my stat menu, and hopefully you guys have been using this already because this is where pretty much everything's going to be. I'm going to go to Z stats. We already know why. This is a Z test. But instead of doing one sample, which is what you've done up to this point, you're going to go to two sample because you're comparing. Now, this is where if you actually loaded the data into Statcrunch, you would do it with data. All right, now because we have the summary stats, the mean and standard deviation, we're going to do this with summary. And then I'm just going to type everything in, right? So my sample one had a mean of 55,950. It had a standard deviation of 6,200. And the sample size was 100. Do the same thing for the second group. I had a sample mean of 51,100. I had a standard deviation of 5,575 and sample size of 100. Now, here's where you want to be careful. Right here, where it says perform hypothesis test, this is where you need to specify if you're doing a left, right, or a two-tailed test. You don't need to change that 0 because you're always comparing it to 0, but you do need to make sure that the symbol that's right here in the alternative hypothesis matches what you have. So if you were doing a right-tailed test, make sure it's greater than here. If you're doing a left-tailed test, make sure it's less than. We had a two-tailed test, so I'm going to leave it at not equal to. All right, I don't need to worry about anything else. I can just leave everything else as it is, and I'm going to hit compute. All right, now what you're going to be interested in are the values right here on the end. So the Z-stat, that's that test statistic. We calculated 5.82. You'll see the same thing here. And then if you're asked for the p-value of the test, which you can compare to the level of significance, it's going to give you that value right there on the end as well. And main thing with the p-value, very small p-values tell us to reject the null. Large p-values tell us fail to reject. All right, so I encourage you to play around a little bit with that too, because it will allow you to either check your test statistic or just more quickly calculate it, especially if you're working from the actual data values. And again, to get that p-value if you happen to need it.